This is a video on tree searching in APL. When we talk about tree searching, we mean to traverse the tree of possibilities for a particular problem or structure. Tree searching is a problem-solving technique because the way you look for a solution looks like the branches of a tree. It even shares common terms with a real tree. Here are the terms I'll be using throughout this tutorial. Since not all branches have the same length, the tree's depth is usually uneven. Some branches may be longer than others. So we have a branch, we have nodes, leaves, roots. We often view trees sideways from left to right. So here we have the root, a branch, some nodes, the leaves. These are basically the only two things to do to search a tree. First, you check for solutions and generate new branches. And two, you search each one of them. This is a recursive process. There are two ways to do this. There's breadth first and depth first. Breadth first, you do all the parents first, then the children, then all the grandchildren, and so on and so on. In depth first, you do a parent, one of the children, one of the grandchildren, and so on. This is the technique we're going to be using for the next problems. Here's an example. This is the entire permutation set of the letters A, B, C. There are 6 possible permutations of the letter A, B, C. For 3 different letters, 6 solutions. For n different letters, you have n factorial solutions. There are other ways to generate all the permutations of a set. Recursivity is an example. It's just one way to do it. I will show you a method to generate all the permutations using trees. Again, there are many ways to do this, but we'll use trees to illustrate the process. So the first step, we generate the new branches. Initially, no letters will have been chosen, and there are 3 possible choices. Those 3 choices are generated: A, B, and C. Step 2, run through each branch. There are 3 branches here. We will have to repeat the process for each one. When we choose A, there are only 2 possible choices left, B and C, and those are generated. We can see the tree shaping up already. When we pick B, there is only 1 possible letter left to choose, C. When we pick C, the only possible choice here, there are no other letters to choose from. This is our cue, in this case, that we have found a solution. No more branches, letters, can be generated. We have tried all the letters of path AB. We now go back to path A and try AC. From AC, only B can be chosen. When we pick B, the only possible choice here too, there are no other letters to choose from, and we have found another solution. We have tried all the letters of path AC and of path A. We will now try path B. Here again, only 2 possible choices, A and C, which are generated. Here, only C can be chosen. And when C is chosen, it is a solution, a permutation. There are no more letters in path BA. We will now try path BC. From BC, only A can be chosen. This is another solution. And we've reached the end of a branch again. Next, the last letter of the first level. From here, only A and B are possible. From CA, only B, and we have another solution. From CB, only A, and after A is selected, no more branches can be selected and all the permutations have been generated. We had to go through all the branches and select all the leaves. So, the 2 steps: check for solutions and generate new branches, and try each new branch recursively. And that's pretty much all there is to it. For this example here, to generate new branches at every node, we chose the letters A, B, C, except those already making up the branch. For example, at level 0, the root, the choice was A, B, C except nothing, or A, B, and C. At level 1, if, say, the branch was A, then the new branches were A, B, C except A, or B and C. At level 2, if the branch was AC, then the new branches were ABC except AC or B. And finally, at level 3, the choice was always ABC except some permutation of ABC, which resulted in nothing chosen. Again, for example, when A was selected from path A, then only B and C could be chosen, as A was already being used. It's a recursive procedure. The code used to try level 1 is the same code used to try level 2 and all the other levels. Here's an example of an APL function that could generate all the letters. The function takes all the used letters and returns all unused letters. Line 4 is where the work is being done. All it does is return the letters not used so far. The check is made on line 6 for an empty unused, instead of checking for 3 equals the shape of used. The same result is achieved. And on line 7, if all have been chosen, the path, the branch, is shown. Note that it is shown only. To gather the result, we would need to store them elsewhere, for example in a global variable. This is the function to search the branch of a tree. Note the recursive call on line number 5. If we were to type that code in APL and use it with the previous generate function we saw, you'd get all the permutations of A, B, and C. In fact, let's try it in APL. Here, let's try this. Yeah, it works fine. Let's try to trace through it. Here, on the first line, we generate a new branch, and if we look at the branch, initially it is empty. If we enter, now we can see that the branch which was empty here is still going to be empty over here. And the unused part will be the letters ABC except nothing, or ABC. Now if it is empty, which is not the case, then it would show it to us, but it won't. So we exit. Now for each new branch, we're going to try each one of them and call ourselves recursively. So now we call ourselves, and the new branch contains now the letter A, which was the first one here. Now we enter generate. Generate now has the letter A as the first branch, and we look at the unused letters, which are going to be B and C. And again, since it's not empty, we skip that code. Go back here. Our branch is A. The new nodes are B and C. We're trying B. And when we get over here, the branch is AB. Now we generate a new branch, which will be ABC except AB, which will be C. This is not empty, so we skip this. We go over here. We have generated C. Now for each new branch, for each new node, we now try the branch which is ABC. We generate the next one, which is going to be this time empty. There's nothing else we can generate at this point. And since it is empty, we display the result in the session right over here. And then if we were to just keep going, we get all the rest. So to recap, know your problem, find how to generate the new branches, find what to do with the leaf. And in the last example, the depth was the same all over. In the next example, this won't be the case. In this second example, we're trying to find all the numbers in a set which add up to a specific sum. For example, find all the unique combinations of 1, 2, 5, 10, 12, and 16 that add up to 28. Now, what we need to do is generate all the possibilities, just like we did for the combination, except that in this case, it's not going to be always the same. For example, 16 and 12 is a possible combination for 28, but so is 16, 10, and 2, and they're different lengths. So how do we go about this? Well, here's a simpler example with 1, 2, 3, 5 that must add up to 6. So for example, we try with 5, and then we could try all the combinations of 1, 2, and 3, and which we actually do. And only the one that adds up to 6, the one in this case, will be kept. With 3, we could try 5 again, but since we've already tried 5 with 3, there's no point in trying 3 with 5 again. So maybe what we should do is just forget about all the numbers that are above the number we're trying, and tricks like this. This brings us to the concept of pruning, which is a technique to reduce the tree size in the search consequently. So to do that, we can select specific branches, we can select a proper number of branches. We may decide that some branches are not worth it. We could order them. There's all kinds of ways to prune a tree. Going back to this problem here, we can see that the 3, 2, and 1 is exactly the same solution as a 3, 1, and 2. So we may want to avoid this and force the solution to only include numbers that are in decreasing order. So the generation function should only generate numbers that are lower than the lowest one that we have in the branch. For example, in this particular case here, which I call the accountant problem, we can select only those which will not exceed the maximum value. For example, if we already know the sum, the maximum number to attain, and the branch contains the numbers whose sum is below that number, then there is no point in generating numbers that will exceed the difference. So if we had a maximum of, say, 28, and the branch contains the numbers 16 and 5, there's no point generating new nodes that will exceed the value of 7. Here's a possibility. This generate function will accept a certain number of numbers and verify that the sum matches those numbers. If it is the case, then we have found effectively a solution. If it is not the case, then we take all the numbers that are possible and only keep the ones that are not above the sum minus what we've got so far. And we should also, in this case, what I'm doing here is that I'm keeping all the numbers that are below the minimum that I have in my list. I'm not reusing any number above, so all the numbers I will be trying will be lower than what I have at the moment. The try branch function is exactly the same as we had before. That one doesn't change from one problem to the other. And let's see it in APL. Here we specify the sum, we specify all the numbers, and we try it. And we could use a cover function like this one here that would have sum as a left argument, all the numbers we want to use as a right argument, and simply calls try branch to solve the problem. One of the problems here is that the try branch program requires the presence of a generate program to work. That name is hard-coded. That prevents us from having several different tree searching programs in the workspace. So we could have another try branch program that would look like this. We could give it the name of the program to use as left argument and use it like this. Here, pname is the name of the program we want to call. It is called on line 1 and used again on line 4 when we do the recursive call. This makes use of execute, but it is more general. For example, if we use this with the accountant program, which is basically the generate function we had before, just renamed, then we should be able to do this. And it works. It used the accountant program instead of using the generate program. We could also use this program, which is basically the generate program, for the generation of ABC combinations, like this. This is more general. If you use an APL that supports operators, we could turn a try branch into an operator requiring a monadic program as left operand, just like this. This operator, try branch 3, takes a program as a left operand and applies it on line 1 on the branch to run. And of course, it calls itself recursively using the same program as left operand on line number 4. Let's try it. It works. Let's try the ABC program. One of the benefits from using this operator is that we can give it any monadic function as left operand. So if we wanted to have a general function that would, for example, give us the combinations of any set, we could do it this way. GenSet is a general version of GenABC. It takes as left argument the set we want to get combination of. So if we use it this way, ABC GenSet, for example the letter A, it returns BC, but it would also work with any other set, DEF. So now what we can do is, instead of using GenABC, this is in Dialog APL. The left argument to try branch 3 is a monadic function. The left argument has already been glued to genset. It has turned it into a monadic function. That monadic function will now be given to try branch 3, which will run it through the entire tree. We should get all the combinations of this, and it works. That sums it up pretty much for this tutorial. There is another problem that can be solved using tree searching, and that's the famous 8 queens problem. I'm just going to show you quickly the result of this function here. So there are a large number of solutions to that problem. I will not show it to you here. If you are interested, there's another video using the same technique as the one I just showed you here that will solve this problem. If you're interested, you should go to this video and you will see how the solution is implemented. So that's it for this video. I hope you enjoyed it. See you later.